Good morning, good day, and good afternoon and good evening to all of you around the globe. Welcome to our STEAM webinar series. And today we're going to talk about steam distribution and consumption in the heavy industries. You're hearing the voice of Oliver, and together with me is Uwe. So Uwe, if you could have a few words about yourself, please.
Yeah, good day, everybody. And my name is Uwe Wagner. I'm at Endress+Hauser Group Services in Rheinach, Switzerland. And I'm in charge for the industry sector power and energy as a global industry manager. Happy to have you all today with us.
Yeah, hello, and this is Oliver. I'm a flow guy, so I'm located in Endress+Hauser Flow, and I'm head of the strategic flow product management for the Vortex and thermal mass flow meters. And I'm looking forward to having you today. And first, I would like to give you some housekeeping. So first, you can find some material. You find today's presentation ready for download as a PDF file. You can type in your questions in the chat box so easily. We hope to provide your answer right now. And the session is being recorded for your colleagues who are maybe unable to make it today. And you can increase or decrease the webcam window, or you can even close the webcam that you don't have to watch myself all the time. Okay, this is part 2 of an entire series. Last week we did talk about steam generation, the boiler house. Today we're talking about steam distribution consumption in the heavy industries. Tomorrow we're going to turn the stuff hygienic. So we're going to talk about food and bev and pharmaceutical life science industries. And on 26th of October, we're going to talk about the condensate recycling, the makeup water and boiler feed water. And module 5 is again the SWAS module, that is steam water analysis systems. So stay tuned to watch the entire series, please. All these modules, they have roughly the same structure. So we're talking about the overview of steam distribution, later on also of consumption. And first we're going to have a look at submetering, the pressure reduction, the superheating and custody transfer of steam. And for each module, we will talk about typical customer pains. We'll talk about the task of the process, what are the measurement parameters, and which instruments can you use, and what are various product advantages. So we are now in the distribution side. So typically you have a steam main header, and from this you distribute to the different points of end use. And you may or may not have the superheating. For instance, if you're taking steam from a higher pressure side, for instance, in chemical plants or in larger petrochemical sites, you have steam for power generation, and from that you get lower pressure steam, so 20 bar typically. And from that, you then reduce even further. If you want to heat some heat exchangers, then you're talking about lower temperatures and pressures. You may or may not purchase steam from an external source. Then you have steam custody transfer. But what you typically always have is internal billing of steam. Then later on, we're going to talk about steam use, the consumption, and typically heat exchangers, but also the fractionating column. So what are typical customer pains? So does enough steam, for instance, reach the point of end use that you are able to produce? The flow measurement downstream of a pressure reducing valve is completely wrong. What's going on? So we're going to have a look into that. How can I reduce the risk of water hammer? Because that's a safety concern, of course. And am I paying for steam or for warm water? Do you get overcharged? Why does your energy balance in steam distribution not match? We first are going to talk about submetering. So submetering means you have your steam distribution header, and from that you pick the steam, you're going to your own consumption also. So you have stripping steam, for instance, that is going back to the boiler house, or also steam for heating your hot well, for instance, and then you're distributing the steam to various end users. Desuperheating, we're going to come to that later on. So what are typical parameters in submetering? So typically we recommend that you, first of all, that you have level inside your main distribution header in order to make sure it does not drown, because this is very important. Otherwise you will have wet steam ending up in your system, and you will want to measure the steam flow to the various points of end use. And you will want to measure the consumption of your corrosion inhibitor. You may or may not inject that at this very point. There are various points in the system where this is typically being injected, depending on the different kinds of chemicals there are about. When we talk about the steam distribution header pressure, and here you typically want to protect that by means of a pigtail, or by YouTube, this is also possible, and you would want to measure that using, for instance, a Cerabar PM51 of ours. Those come with SIL certificates, and they have very easy setup. Meanwhile, they even come also with Bluetooth communication. When we talk about the level switch, here we have high temperature switches. So you see here the FTL 81. Alternatively, we also have 71 or 6264. So Endress+Hauser actually is the main producer of vibrating forks when it comes to these high temperature switches. When you want to measure the flow to the various points of end use, there it's very important that you compensate by pressure and temperature, and that you compensate by the dryness fraction. Why is that important? First, you may have wet steam, because this is the classical case. You have wet steam if everything is working nicely, because you have saturated steam already sitting here, and it's not perfectly dry when you send that to the different points of end use. So you want to know, how much dryness fraction have I got? And we learned last week about the importance of the dryness fraction. It has two effects. It's A, the efficiency itself. So if you have a steam that is only 95% dry, you already have lost 5% of its available energy. It's HFG. On the other side, the dryness fraction has a negative effect on the accuracy of all those flow meters that are out there. So we have seen that for a typical vortex meter, if you have a 90% dryness fraction, classical vortex meters, they will experience an extra error of 5% in mass terms, and an orifice plate even will experience an error of 7 to 8% per ISO 12767. So on the other hand, superheated steam may occur as well. Why? Because you have these valves sitting here, these isolating valves, and in case you don't open that fully up, what's going to happen? You throttle, and this throttling effect is going to result in superheated steam. So you have relatively dry steam sitting here on that side, and if you throttle that very far down, what's going to occur? You reduce the pressure, and then you're going to get superheated steam, and only the Probel F200, then it can tell you how many degrees of superheat you have. So this is very helpful there. You always know where you're at on the Mollier chart. Here's an example from a chemical industry from Australia, Borden Chemicals in Brisbane. And here we see saturated steam. Here you see a smaller line. This is the own consumption going back to the boiler house. And they have remote electronics for easy access here. So that's a nice application picture, I would say. A problem that typically occurs in steam lines is water hammer. And here in this case, this customer experienced condensation-induced water hammer. What was the problem? You see we're here at the low point, and well, that's good practice. They have a steam trap sitting here. They have a T-piece with a steam trap. But the problem was that steam trap was not working. So the entire section here was drowned, and steam was coming in after the weekends, and then you had condensation-induced water hammer. That means you had a collapse of that steam bubble that came in, and that resulted in huge impacts that even killed the old version of our sensor. Meanwhile, we have changed the sensor. We have an improved design of our sensors. And this is something I can show you here. We did intensive testing on these guys because we introduced that new generation only 3 years ago. So let me show that to you. So we go to this video. So this is available on YouTube. You can easily find it by entering condensation-induced water hammer test, then Endress, and you're going to find that. First, you see how a water hammer looks like. First, here we see some slug flow water hammer. This is not what we're talking about here. We're talking about condensation-induced water hammer in this test. So you have water, and in that water, you have a bubble of steam, and that then collapses, creating vacuum. This is what you've seen right now. And now you see how that test is being done by our R&D. So we have a steam generator, we have a steam pressure of 3 bar, which is 45 psi-ish, and we're sending that to 2 sides, and on each side you find a bucket of water. So that steam is going in here, and when we close the steam supply, what's going to happen? All of a sudden we create some vacuum, and we suck the body of water on each side through our device here. And you just see the pressure gauge here showed a small change in pressure. Well, the reality is we got pressure surges of 280 bar. So that's 100 times these 45 psi we've just seen. So 4,500 psi. This is incredible in such a low pressure steam pipe. And this is a huge impulse, of course. And even though we repeated that test various times, we got no failures of the sensors. So this is a great thing. Meanwhile, we have a lot of cases where our meters also replaced competitor devices like competitor Vortex meters, or also here, this is a case where we replaced a mechanical device, so a mechanical spring-loaded orifice plate, they call that. And that failed immediately after one single water hammer. And they replaced that using our Probel F200, and they didn't have a single failure ever since. In refineries, we have replaced an entire series of competitor makers' products that kept failing on a regular basis, and they haven't had a single failure ever since. So this is the beauty here. So when we go further down the line, we go into the amine tank. This is for corrosion inhibition. So it may be at a different point in your system. So here you want to do some inventory management, and in doing so, you need some level measurements and you need a flow measurement. For the flow measurement, typically you're talking about small amounts. So here we recommend, because that chemical is typically expensive, using a Coriolis meter for best accuracy. And those are available also, you know, for small line sizes. So 1 millimeter, 2 millimeters, that's easily done. And for measuring the level, here we have a very nice new device. That's the MicroPilot FWR30. This is an IIoT radar. So this guy, you can connect directly to the cloud and to Natillion, our cloud service. And then you can automatically also call, so to speak, the chemical supplier and get a new tank of that stuff that you can keep producing, which is of course important. Now we're going to talk about the superheating. So what's done in the superheating? You send superheated steam in and you get steam at a lower temperature out. So in the US, it's often called an attemperator. And you reduce the temperature of that steam by adding cooling water. What's the reason? Typically, you have a lot of applications where you have steam at a high temperature available, but you need steam at a lower temperature, at a much lower temperature and pressure. And there, this is the perfect solution. But what is not so easy, it's creating an energy balance across such a guy. So for that purpose, what is ideal, especially at the outlet, I recommend to measure pressure and temperature and the dryness fraction. We're going to come to that. Why? I would measure the pressure of the superheated steam coming in and pressure, flow, and temperature of the deionized water coming in. Also, the quality is very important, but we're going to cover that in our module 5 in the SWOS section. When we talk about the deionized water, here we recommend to measure the pressure using our Cerabar, the PNP 51 new generation 51B. Then the temperature of deionized water, here you would use our Moduline TM131. And for the flow, you can use our Vortex meter, the Probel F200. You can even use that with an integrated temperature measurement here at that point, or even with integrated temperature and pressure. This is also possible. So then you can actually output the energy of the feed water, of the deionized water you're sending to that thing, and for your energy calculation. We're coming to the saturated steam flow measurement. Here, best solution again is to compensate by pressure and temperature, because typically that steam is going to be slightly superheated that you get out, because you have some inlet lengths till you actually reach your point of end use for the steam. So ideally you would allow for some degree C of superheat here. But in some cases, if you add too much water, what's going to occur? You're going to see wet steam. And our Probel F200 is really ideal for such an application, because on its display and on its output, you can assign the dryness fraction and the degrees of superheat. So it's a quality meter that happens to measure flow as well, so to speak. So here you see you have the dryness fraction on the display. Here in this case, it's 100% dry, and we have 24 degrees C of superheat, 24 kelvins. And here another case, you see steam is wet. We have 93% of dryness fraction and 0 kelvins of superheat. So ideal for these cases, and it compensates directly both mass and energy using these information. Now we're talking about pressure reduction. So especially if you have, for instance, now steam coming from a 20 bar grid, and you need, however, steam at 3 bar. What do? You reduce the pressure. So the superheater reduces temperature mainly. Pressure reduction reduces pressure. So what you do is typically you first send the steam through a separator that takes moisture out, condensing moisture. You have a steam trap located here, and then you send that steam through the pressure reducing valve. Downstream of such a combination, you will expect always superheated steam. That's why you should always compensate by both pressure and temperature. In reality, however, many customers are compensating by temperature only because it's cheaper. But that leads to completely wrong measurements. You can have errors of 40% or even 100% easily, typically over readings, because you then take that temperature reading of your superheated steam and you assume this is your saturation temperature. But this results in completely wrong densities, energies, and so on. Don't do that. Compensate in such a layout always by pressure and temperature. And in addition to that, please always also compensate by the dryness fraction. Why do I say so? I just mentioned it's superheated steam. Well, in theory, yes, and not always, because don't forget you have a steam trap sitting here. This is problem number 1. Steam traps are mechanical devices. So if you don't properly maintain these guys, you will have cases where these fail. And what happens then? Your separator is going to drown, and you get wet steam in, and you also get wet steam out. If you don't have a separator, even worse. What happens then? You're sending, for instance, 90% dry steam into the pressure reducing valve. You're reducing that from a 10 bar pressure, 150 psi, down to a 3 bar pressure, 50 psi-ish. And what's happening? You increase the dryness fraction only slightly. You're coming from 90% to 92%. So it's an isenthalpic expansion that you're doing. So very important point. Please keep that in mind. Another problem is those separators here, they come with a certain specification. So in theory, they may be good down to a steam quality, a steam dryness of 95%. They really specify how the amount of moisture they can take out of the system. But if you have more moisture coming, what's going to happen? You keep that in the system, and this is going to end up downstream. So you expect to have superheated steam, but in reality it's wet. So therefore, please, in that measuring point also, I recommend clearly to measure pressure, temperature, and the dryness fraction for compensation purposes. So this is, in these cases, very, very helpful. And once again, don't compensate by temperature only here. Please don't. And using applicator, we don't have the time. You can even estimate the error you're making in case you compensate by temperature only. And easily, I can tell you it's 40% up to 100% or even more. Here you see an application example. Here we have a vortex meter of ours downstream of a dryer and a pressure reduction. And the dryer here, in this case, it can be switched on and off, an interesting one. So here you see typically the steam dryness fraction of the main line is 90%-ish. And when you switch on the dryer, you see the dryness fraction increase from 90% up to, yeah, we're going to end up close to 100%. So you can also see the amount of information you can actually assign to the display. So you can assign the dryness fraction, you can assign the degrees of superheat. Here they have the velocity. You can assign energy in megajoules or MMBTUs, or mass in tons per hour, totalizers, whatever you like. So plenty of information that is available here from that device. So I'm going to move on. Here, next topic is custody transfer. Once again, custody transfer is relevant if you're purchasing steam from an external source across the fence and you have to pay for it. Closely related is the topic of billing, of internal billing. And classically, you find in custody transfer applications for steam, you find very often DP layouts. So for these cases, you can use our Delta Bar SPMD 75, new generation PMD 55B as well. And pressure and temperature compensation here, I would always use the best pressure and temperature devices. So the Sarah Bar S, this is the highest accuracy that we can offer, and Omnigrad TR15, this is a weld-in temperature sensor. So for these higher temperatures typically, and you compensate inside of your computer like the NGCAL RS33 that's coming with IAPWS data. So like the vortex meter that is saving using the same data. So orifice plates are standardized in the ISO 5167. For vortex meters, there's also a standard available since 2017. I was on the standard committee. So that's the ISO 12764. And our vortex meter is, of course, complying to that standard. And I recommend for custody transfer of steam to use our vortex meter with integrated pressure and temperature and the dryness fraction. Why? Because only if you know the dryness fraction and you have steam that is actually at the saturation line, only then you will know if you're charging or getting charged for hot water or for steam. Because if you measure 180 degrees C and 10 bar, for instance, you think, okay, that's saturated steam. It's I hope I have 100% dry steam. But in case that is only 90% dryness fraction, same pressure and temperature, you would get overcharged by 10%, so to speak, because you are paying for all the warm water you're getting as well. And only that vortex meter can actually tell you, with that dryness fraction, what am I really getting? What is really in that pipeline? And in addition, in case you have a contract for superheated steam and you have a guaranteed amount of superheat, you can always check that and you can use the output of that vortex meter to say, hey, Mr. Supplier, I'm getting overcharged because my steam for 15 hours last month was less than 5 degrees C or 5 Kelvin superheated. So that really gets rid of that doubt if you have, or if you are receiving steam or hot water from your supplier. So that's really the best solution for such cases. So here we have a nice application example. First, that's an example from Czech Republic. The Czech Republic is one of the very, very, very few examples worldwide where you have a national custody transfer standard for steam. Because keep that in mind, there is no OML standard for steam right now. So which is, of course, a stupid thing, because you often pay for steam, you get charged for steam, but there is no OML available. But in Czech Republic, it's slightly different. But our meters are certified for this national approval, the GMI, the Czech Metrology Institute. We have those approvals available. And this is another example. This is internal billing in a huge steam plant in ArcelorMittal Zenica. This is a huge steam grid. It's about 2 kilometers long, and they are billing internally about 40 cost centers, and they're using the steam measurements using volume, pressure, and temperature. This was done some years ago. Meanwhile, I think we will do that using the multi-variable version and not compensate inside those flow computers. Here an example also from the oil fields. This is distribution inside EOR, so enhanced oil recovery, where you're sending steam into the ground in order to get heavy oil more fluent, so to change the viscosity, and then you pump it out. The right-hand side is in the desert, so to speak. I think that's in Kuwait. The left-hand side is in Siberia. So we find those devices in a variety of climates. And here is a special meter we did for Canada, for SAGD, for the oil fields in Alberta. And this is made of carbon steel with a special means to check the health of the beloved body. But this is a requirement per AER Directive 17, so a local requirement in Alberta. So let's come back to our industry observations when we talk about steam distribution. So does enough steam reach the point of end use? We recommend to measure pressure and level of the main steam header, but also to check the dryness fraction of steam in the different distribution lines, because that helps you to check the energy along your entire distribution system. Your flow measurement downstream of a pressure reducing valve is completely wrong. I think we covered that for a while. So the steam here could be wet, it could be superheated. And then it's important to know dryness fraction and the degrees of superheat. And in general, this is so funny. Actually, in all parts of your system, you can have steam either superheated or wet. So it always makes sense to know degrees of superheat and the dryness fraction, because as one of the two can be an undesired occurrence. So only if you measure it, you can control it. How can I reduce the risk of water hammer? Well, here measuring the dryness fraction provides you an alert and an early warning, so to speak. And also this main steam header level switch is very helpful here. Then are you paying for steam or for water? Do you get overcharged? Again, measuring mass flow and the dryness fraction, that will ensure you're getting the energy you're paying for. So this is also very important. And you get proof. What are you getting really? And then why does your main energy balance in the steam distribution not match? So a very common problem is that people are using older meters and those don't come with the compensation of the dryness fraction. This is very often the problem. And if you don't know the dryness fraction, you don't know really the energy that is contained in your wet steam. This is very often the main problem that I've seen in their system. Is your steam superheated, saturated, or wet? The Probe, our F200, it can't tell you so. So that really tells you on a map where you are on your Mollier chart, so to speak. And how can you optimize the control of your superheater? Here again, it's important to know the state of your steam at the outlet of your desuperheater. that you control ideally the amount of deionized water going into the desuperheater or temperator. Now we're coming to the steam use, so the steam consumption. A friend of mine, he said, steam generation in the boiler house, this is where you burn the money. At the heat exchangers, this is where you're wasting it. So we're talking about this waste, so to speak, now. And typical pains in the steam consumption are how efficient is your steam consumption. Efficiency is very important here. How can you avoid product loss through overheating or through underheating, so to speak? How efficiently is your heat exchanger operating? When should you clean it or backflush it? And typical heat exchangers, there's a variety out there. You find very often the shell and tube heat exchangers in the process industries, plate heat exchangers too, depending on the cleanliness of the fluid. So plate heat exchangers are also very common, by the way, in the cleaner industries. So ideally, in both cases, what's happening, you have perfectly saturated steam entering here. This is ideal. Reality, however, is you have superheated steam or wet steam. So you have neither. Therefore, it's very good also here to know what is exactly the energy content of my steam. Inside the heat exchanger, sorry for that, oops. The latent heat of the steam is passed on to the process. So the HFG is passed on and you have condensate coming out. So HF is leaving the heat exchanger. And on the product side, you have a cool product that is entering the heat exchanger and it leaves it at a higher temperature. So the measurement here is pretty evident. I mean, it of course is important that you measure pressure and temperature because you may have superheated steam at this measuring point. Too much is no good. So if you're coming out of a PRV and that is working, then you may still have superheat here at this point. So up to 15 degrees C of superheat is typically still okay because then you allow an extra size of your heat exchanger, but you must watch out that your product can abide 15 degrees C of superheat. This is also important. And often also you find that the steam here is wet. So again, important, measure the dryness fraction, measure pressure and temperature to know where you are on the Mollier chart. And if you want to know the energy that you pass on to your process, I would read in an external temperature. You can use such a skin temperature measurement here. This is something we are providing and read that in using the 4-20 current input into the Vortex meter. You can also use digital input, then you know the energy. How much HFG are you passing on reality to your heat exchanger? So again, Probal F200, best solution for such a case. Just a side remark for cooling applications, this is pretty similar. You would want to know the energy in versus the energy out. So you then can calculate the heat exchanger efficiency. And this energy calculation, energy out versus energy in, is more accurate actually than just using UA values and the delta temperature. So this is a clear recommendation. Then from a quality standpoint and also safety aspect, it makes sense to check turbidity if you're measuring oil inside such a heat exchanger, because in case the turbidity is changing, then our turbidity sensors, your OUSTF, can tell you about those changes. In case it's conductive fluid, then you can also use the CUS 52D. And then you get decontamination and get a warning in such cases. On the product side, this is classical Endress+Hauser business, of course. When it comes to oils, hydrocarbons that you're heating, then you would use a Coriolis meter, so like our ProMass F or even better, the ProMass Q. That is a very nice, relatively new device, or the ProMass I, that not only provides you measuring of mass and density, but also the viscosity. And for conductive fluids, of course, you would want to choose a mag meter like the ProMag P200 or P300. Okay, let's come to the fractionating column. Fractionating columns are used for separating the crude oil stream into a variety of products like gasoline, naphtha, kerosene, gas oil, and so on. And you have a lot of steam being used in such an application. So you find heat exchangers for the preheating of the product. So those are typically shell and tube heat exchangers consuming steam. Exactly what we've just described. You would use the probe here to check the amount of steam going and amount of energy going into such a heat exchanger. Then you go through a heater, a furnace, and then you also have stripping steam here. So that stripping steam is injected directly into the flash zone, and that helps the separation process, because the hydrocarbons, they are non-polar. The steam is a polar molecule, and that assists in the separation process. So here you see the three zones of such a fractionator. You have at the bottom the stripping zone, where you're sending in the hot fluid, so heated by a heat exchanger. So here you're sending in stripping steam. Then you have the flashing zone. Here you're sending the feedstock in. Again, here we see the heat exchanger using steam with the flow measurement and delta T. And then you know the energy. And typically here on the side you find also reboilers, especially here on the residue and bottom side. And those also consume steam. So a lot of steam being used for the stripping process. This is direct injection. This is a little different. So here for the heat exchangers, you would measure the steam flow, but also temperature and pressure and the temperature of the return condensate in order to check the energy. So a lot of other measurements, of course, are involved from our side. You see, like for the mainstream, typically you find our Coriolis meters, temperature, pressure. But another important measurement, I'm going to come to that, is here the guided wave radar for the bottom zone, for the bottom extraction for the residue. So typically you're going to end up with the FMP54 in that case. We're going to talk about that. Then here we see for the stripping steam measurement, you need a vortex and pressure and temperature. And meanwhile, our recommendation is to use this guy with the integrated pressure and temperature measurements, because then you also know the dryness fraction of the steam, because the dryness fraction, again, for the heat exchangers, but also for the stripping steam, has a lot of meaning, because only then you know the true energy of that steam going into your fractionating column. And this is something only Endress+Hauser can actually offer you. And here you can actually see what wet steam looks like. So here we see 100% dry steam. This is, it looks like a gas, so you can't see anything. 90% dryness fraction in a horizontal line. You get a stream of water forming down here. And at 80%, you get annular flow. And in the middle, by the way, at 80% dryness fraction, you don't see anything. There's, in the middle of the pipeline, there is no moisture condensing there. It all condenses on the pipe wall, interesting enough. So I was mentioning the FMP54. This is our guided wave radar. So this is also used in boilers, but also at the bottom of these fractionating columns. And something that is used more and more also in these applications, that's the heater scheme temperature. So in these furnaces, for instance. I'm coming back to the typical pains at steam consumption. So first, how efficient is my steam consumption? And we know superheated steam and wet steam, neither is good for transferring heat. Too much superheat, we keep in mind 25 degrees C of superheat is too much, 15 degrees C is acceptable. And if you have wet steam, that has already lost part of the energy. So we must control the steam supply in such a way that we're as close as possible to the saturation line. So in most applications. And ensuring dry saturated steam at your heat exchanger will ensure optimum performance. However, true dry steam does not exist. So this 100% exactly, this is really like reaching the sharp edge of a knife. Imagine a steam distribution line. You keep distributing the steam and you're losing energy. So first it's superheated. You may still have maybe 5 degrees C of superheat, then you're losing more energy. You have 4, 3, 2, 1, 0 superheat. You're exactly at the saturation line, but that's very microsecond. I say that. In the next moment, you have already lost more energy and you are in the wet zone. So there is no saturated steam. In reality, there's only wet steam or superheated steam. This is very important. This is again why these outputs of the degrees of superheat and of the dryness fraction of the vortex meter are so important. And balancing the steam production and distribution, that gives you insights in the inefficiencies of your process once you know the dryness fraction and the degrees of superheat. And the wet steam and fractionating columns, it not only reduces efficiency, but it can also damage columns because of water hammer, obviously. So this is very important to know. How can you avoid product loss through overheating or underheating? So this is exactly by knowing the right measurements. So knowing the right degrees of superheat and by knowing the dryness fraction of your steam. Ensuring clean dry steam to your heat exchanger, then you make sure that you have optimum heat exchange. So how efficiently is your heat exchanger operating? When should you clean it? Using the memograph, you can really monitor the efficiency of your heat exchanger. You can check the energy in versus energy out over time. And in case something is wrong, you will see a drift in that value. And then using that balance, I would not only use temperature. I would use the true energy. The measurements are there and they are offering you a better solution, a better measurement to know when it's time to clean your heat exchanger. So Uwe, did we get any questions? Because we're almost at the end of our session.
Yes, Oliver, we had great attendees. There's only one question. Seems to be everything has been explained crystal clear. The question is, can I have the handout? And where, or is it possible to see the recording again?
Okay. Well, the handout is available in the handout session. So if you're with us right now, you find that on the right-hand side of your control panel of the go-to. So do so now. It's still time. And the other point is, if you want to watch the recording, it's very easy. You can just follow the link, the original link of this very seminar, and you can forward that to colleagues. They can sign up for it and watch the recording at a later point in time. This is not a problem.
There's just coming a feedback in from Jeff. Jeff is writing, the information is excellent. Very good to know about steam quality and ensuring we are not buying hot water.
Yeah, absolutely. I couldn't agree more with you, Jeff. Very good statement. Yeah.
Good.
Thanks a lot for that.
There is nothing more that let's finish 2 minutes earlier. It's also fine. No problem.
Also good. Just a lookout maybe for the next series. So in case you're also involved in hygienic industries, I mean, very often, typically the guys in heavy industries, this is why we separate the sessions. They're not too interested in the hygienic industries and vice versa. So tomorrow we're going to talk about steam in hygienic industries, food and bev and life science. And on 26th of October, we will talk about condensate recycling, makeup water and boiler feed water. And last not least, on the 28th of October, we'll talk about steam water analysis systems, SWAS. So 28th of October, this is going to be done by Uwe Wagner and by Daniel Schweitzer. I'm also looking forward to this session. And last not least, yeah.
There's a last-minute question coming in, Oliver.
Okay.
Is it possible to measure steam traps condition? Question from Darzo, sorry.
Okay, there are typically what you do for monitoring steam traps is for especially those thermodynamic traps, you have ultrasonic shotguns, so to speak, and with those you can check if they're still alive. What you see indirectly is if your heat exchanger is being drowned, you could place a temperature measurement, so to speak, a little upstream of the condensate trap. So you see if that's cooling down. In that case, you know, oops, I'm drowning, my heat exchanger is drowning. Or you place a level switch inside the heat exchanger. We've also done that in some cases. This is an indirect measurement. Or you can also check, or what is not possible is the flow downstream of the condensate trap. Why? Because you're exactly in the flashing zone. So even using a flow device without pressure drop like ultrasonic, it doesn't help you because in that case, you always have two-phase flow. So you either monitor the steam trap itself with a shotgun, or there are also solutions available from a company like SteamIQ in the US that are checking and monitoring the health of those steam traps on a continuous basis. So this is also something that is very helpful. Those are connected then via LoRaWAN. SteamIQ is the name of the company. So this is also possible. Yeah.
Thank you, Oliver.
Very good.
Then so, we are at the end of the session.
Very good. Yeah, just keep in mind we have a nice full portfolio to increase safety, efficiency, quality, and availability in steam. We talked today again a lot about Provel F200. We will cover SWOS in a later stage. We talked about level flex FMP54, so with the gas phase compensation as well. And we did cover today the FWR30, the IIoT radar. So looking forward to having you in our future sessions. Glad you made it today and have a very good one. And oh yeah, I just see somebody's asking for a certificate. Yes, you will get automatically a certificate from GoTo. So this is coming automatically. You will get that tomorrow. Okay. In that case, have a good one. And thanks a lot, Uwe.
Yeah, thanks, Oliver, for all these insights. Very helpful for the audience. They are writing.
Thank you. Okay.
Stay tuned. Take care.
Bye-bye.
Stay healthy. Bye now.
Bye.